Okay, I think we're top of the hour. Good morning, good afternoon, good evening, wherever you are.
So welcome everyone. This is the Computing in the Network Research Group meeting with Jeffrey He, Yves Schooler, and me, Marie-Josée Montpetit. We are the chairs of this, I think, exciting research field that I think is more and more important in the development of the internet. You move the slides, Eve. So
Can you hear me, by the way?
I think everybody is aware of this. I think for this group, yes, it's important, but also you know that we're recording this because we are still virtual, and I guess even when we'll go not virtual, we'll do it. I think what's also very important is all the disclosures of intellectual property, which is on the next slide or something, and the code of conduct, which is also very important. And I think a few of us have had experiences that show us how important it is. Eve, maybe you want to go to the agenda very fast?
Sure. Can you hear me, my audio? And can you hear me? Am I not on
the slides?
Yeah, I think we can
yes,
hear
so
you.
this is the
oh, you can hear me.
policies,
Okay.
Harassment, copyrights, and everything. Next one.
Sure.
But
So,
maybe Marisha,
another
they cannot
thing that I
hear
think is
us.
very important
Okay.
because we are meeting at the same time as the IETF, but the IRTF is not there to do standardizations. It's there to conduct research, and you will see from the agenda you you will see from the agenda that there are important research papers that are going to be presented today. And I know there was an audio issue, and I think I fixed it. So thank you for the people who mentioned it. Next slide, Eve. So we have a very packed agenda. So, you know, I'm already 2 or 3 minutes into this, so we're going to go very fast. I think we're very, very happy to have Scott Schenker to present the Extensible Internet, which was a CCR paper, and it essentially raises a lot of interesting questions about the future of the internet, and also is connected to some of the questions that we've had in this group. So we're very lucky with this. Then we have the very interesting in network aggregation paper, then also the information-centric data flow for distributed computing from Dirk. And we had, well, it's actually IDs, but actually there's only one. Alessandro, because it's a holiday, is not going to present. I'm going to present this. It's about an operating system for distributed applications. And in Coined, we are very big on thinking that the internet is moving to be more like a computer board. And if we have a computer board, you need an operating system. Next slide. Then we have the drafts update. Obviously, a research group is not about doing only drafts, but we do have very interesting work that is happening in the drafts with this research group, and we would like to give them a chance to talk about the ideas. So use cases, again, to show that there's a way to use these things. Transport protocols, because also this has been an issue once you start putting computing in the system. And then the security and privacy, and again, a big issue. We have a new draft that was submitted by China Mobile. And then we'll have, we would love to have 10 minutes left to talk about future groups and future meetings and what would like this a little bit to evolve into. But I think the main goal is to have the papers presented. So we're going to do this. The Meet Deco, please
you found us, you're here. This is good.
Yeah, it's found, if you're there, you found the Meet Echo, which is good. The live minutes, it's integrated to Meet Echo, Codim, the mailing list. Well, if you're here, you probably know about our mailing list. If you don't, well, please do that. And, we have a ton of documents. Dirk, your document expired and needs an update because it's an RG document. We have 2 RG documents. We have, again, new drafts. I think this needs an update because we have the new draft from China Mobile also. And we have a ton of other drafts that are at different level of maturity, and essentially this is something that we will raise on the list, the idea that we need to do something about it. The milestones, we've done a lot of it, and we need I'll go very fast because I know I'm 1 minute over. We'll go very fast to the last thing, which is we need a milestone review, and we'll do it. And now we have the presentations. And the first one is Scott Schenker from Berkeley on the extensible internet. So Scott, thank you very much for doing this because it's so early in California.
Well, thank you very much. Let me share my screen. I don't see.
Oh, here. No, it's coming. We just clicked on share screen.
Oh, okay. Good. Do you see it again?
Yes, here, let me give you permission. Is it coming up?
Okay, can people see this?
Yes.
Okay, well, thank you very much for inviting me. I'm typically up at this time, so this is not a problem. This is based on, I'll be talking about the extensible internet. This is based on a CCR editorial with 18 authors. There's a much smaller group that is trying to actually bring this into reality. And I gave a talk on this at another research group, and so I apologize for people who saw that talk, Adrian and others, but this will be large overlap. But the goal of this talk is really to give a very, very brief overview of extensible internet, just enough to initiate a discussion, both about the merits of the proposal, but also how it relates to the charter of this research group. And obviously more details would be available in follow-up conversations. So the core subject of the talk is really about architectural change. So when I say the word architecture, I'm really referring to the arrangement of the data plane functionality. That is the layers and the basic functions they've been assigned. It's not about specific protocols. IPv4 to IPv6 is not an architectural change in my lexicon, nor is it about the control plane. Now, there's been decades of architectural research trying to make changes to the basic architecture, but I think it's pretty clear that over 20 years of clean slate architectural research, there's no discernible architectural impact. And the public internet, at least in the eyes of certainly the researchers I talk to, seems doomed to architectural stagnation. That we've tried, we don't see any movement. But that's not what the hyperscalers think. The cloud and content providers are building their own large private IP-based networks. They've got many points of presence. And what's relevant to this working group, these points of presence apply extensive in-network services, flow termination, caching, load balancing, and so forth. And these services have had a very significant impact on customer latency and reliability. So they put a lot of money into it because they actually see very tangible benefits in their user community. Now, this is great for applications. Users get much better service, but it's bad for the internet. Because the internet is becoming increasingly balkanized. These private networks are defining their own in-network services. The public internet, which can't do this kind of interposition, is lagging behind. So that we're in a situation where the benefits of in-network processing have been shown, but the public internet can't do it because it's not part of the architecture. So rather than these ad hoc and proprietary designs, what we need is to figure out a way to build this coherent, this in-network processing into a coherent architecture. And you might say at this point, but didn't you start off by saying the internet is impossible to change? So, what's the deal? And so we don't think it's impossible to change, even though I've failed personally many times in the past. But this talk is about why we think there's a chance. And so the rest of the talk, much like a Seder, is going to be organized around 4 questions. Why is the internet so hard to change? How can we overcome this barrier? What would this new internet look like? And given the failures of the past, why do we think now is different? And so for the first question, you know far better than I do about the architecture, but let me just review one of the critical aspects, which is that layer 3 has 2 roles. On the one hand, it was designed to allow layer 2 networks to interconnect. And therefore, by definition, it must be in every router. That makes it almost impossible to make change. That is, it's in too many places. It's got to be implemented with very good price per performance. So it's typically baked into hardware. So changing that is impossible now and in the future. I don't see that changing. On the other hand, it provides the service model to host. That is, this best effort packet delivery is exactly what anything you want to do on a host. That's the service that you see and you have to build on. So it has to support all application requirements. And these requirements are becoming more stringent, which is a reason to change the architecture. And that's exactly why these hyperscalers have built out their own networks to extend the architecture for their own purposes so they can meet these requirements. But it's this dual role that prevents change, because you have demands coming from above, you have constraints coming from below, and they are meeting in the middle in a single layer. So the network must meet additional application requirements, but the only layer that can address those requirements is also the only layer in the architecture that can't be changed. So that's the nub of the problem, that they coincide in the single layer, both the demands and the constraints. So the second question is, well, how can we overcome this barrier? And this is where the extensible internet proposal comes in. It's really very simple. You use the current IP protocol unchanged. You don't do anything. But you do introduce a new layer above it. We call it service layer or L3.5. And the service layer offers new in-network services to hosts. So this is the relevance to this working group, is this in-network services. This is flow termination and caching, and beyond, which I will discuss later. And the point is, this is really the architecturally coherent version of what's going on in these private networks. This is really trying to articulate how to think about it in a coherent way. So why does this solve the problem? Because it decouples layer 3's 2 roles. Currently, it's the interface to both L2, which gives it the constraints, and L4, which gives it the demands. And in EI, L3 is still the interface to L2. It does a perfectly good job of that. But L3.5 is the interface to the hosts. And there's no reason for L3.5 to be in every router. It can be much more sparsely deployed, so it's more easily deployed and changed. And at the same time, there's no reason for it to be narrow, so it can meet a wide range of needs. So we've separated the constraints from the demands. And so now L3.5 can meet those demands, while L3 is meeting the constraints or obeying the constraints. So what would this design look like? You have a service layer, SL. It's implemented in what we call service nodes. These are racks of servers deployed at the network edge. And here by edge, I just mean somewhere close to clients. It's not at a particular place in the network. Every host is associated with at least one and typically several service nodes for reliability. And the typical communication pattern is packets go from the source to the service node associated with the source, to the service node associated with the destination, to the destination. All the service layer communication is tunneled over IP, and the source specifies which service to invoke using the tunneling protocol when the packet gets to the service node. And it's this ability for clients to signal to the service node what service they want that allows this to go beyond what the hyperscalers are doing, which needs to be backwards compatible, to actually, we're able to offer services like multicast where the host needs to know that you've changed the semantics of what they've asked. So this is the basic outline of the design. This diagram is just telling you that no matter whether you're in home or office or a cellular network or in a car or in the cloud, there's a service node nearby that will mediate your communication. Now, the key point here is that all these services, that these in-network services that I talk about, are in software. So standards are not detailed written specifications, they're open source code. And there are three necessary software components on a service node. One is the service modules. That is, for every service, whether it's multicast, whether it's DDoS protection, there is a service module that's implemented that's running on a service node. It runs in a standardized execution environment. This execution environment has a very simple set of primitives: packet in, out, ephemeral storage, stable storage, maybe one or two others. But it's a write once, run anywhere environment. If you write your service module to run inside this environment, it can run on any service node. And then, of course, in the service node, you need some kind of runtime or orchestration to scale up, scale down, recover from failures. This doesn't need to be standardized. You know, there'll be open source versions available, whether it's Kubernetes or OpenStack or whatever comes next. And when I talk about in-network services, this is limited computation. This is not where you run your machine learning jobs. This is basic packet forwarding, payload processing, simple functions like caching. So it's more complicated than just simple IP forwarding, but it's not general computation. It's fairly limited. And these service nodes don't just have to be generic processors. They can have secure enclaves, they can have hardware accelerators, but everything you do has to run on a commodity processor. But if there happens to be an accelerator, that can be used to get better performance. Now, choosing the services, this is where you have some kind of governance process, whether it's IETF or something else. You know, it's way too early, but there's some body that decides what are the set of public services and their implementations. And all of these public services are run on all service nodes. That is, if you're offering internet service, so you're supplying a service node, you have to download all of the service modules that are in the service model that have been approved. And so this is really the biggest change to EI, meaning that EI brings this deployment model that is, because they're approved software modules, they can be rolled out, they can be deployed. There's no per vendor, per domain decision process of, is Cisco going to support this? Is Juniper going to support this? Then is AT&T or Deutsche Telekom going to deploy it? It just gets rolled out as part of the standards process. Now, so after all this talk about, you know, the process, what are the services that might get offered? You know, they're the basics like flow termination and caching and load balancing, which you already know bring a tremendous amount of value. There's support for other delivery models, multicast, pub/sub, redirection, QoS, and QoS here not in the in-serve, diff-serve kind of QoS, but in the SD-WAN kind of QoS, that you can pick paths or different delivery vehicles that meet your needs. Support for security and privacy, it's very easy given this architecture to build a very good DDoS prevention. But also if you have secure enclaves, you can have scalable attestation so that a client, when it's accessing Google or some other hyperscaler, can be assured that it's dealing with a legitimate node that is running the current Google software. You can have ODNS-like privacy, Tor-like privacy. You can also incorporate other frameworks that are becoming quite popular. They can be running on these service nodes, Istio and then OPA for the policies, various telemetry kinds of frameworks. And then support for radical new architecture, something like ICN, whether it's the DONA style or the NDN style. This now just becomes a service. You just roll it out. You're not replacing all the routers. It's just a piece of software. There'll be host support, obviously, of course, for all the services. And this just gets rolled out like another standard. So it really lowers the bar to this deployment. And that's why we call it the extensible internet, because once you get this framework set up, it makes it very easy to extend the service model in rather radical ways. And so the
Scott,
last question.
I have a question
Yeah.
for you. Would you like to take questions from the audience now or at the end?
I've only got a few more slides. Let me take it, let me finish, just because
Okay,
then
sounds good.
I think we'll have the context.
Okay.
So given the failures, why do we think this might succeed? And there are three reasons. One, backwards compatibility. IP just continues to be used. If you don't want to change anything, you just use IP. You know, maybe 20 years from now, that'll go away, but when we roll EI out, nothing changes about IP. And the kind of resources you need, you just need the service nodes, which could use edge computing or existing POPs. They have these facilities out there. I mean, we've talked to some carriers and they say, yeah, you know, we could run this tomorrow, that we've got all these facilities available. Obviously, there's more involved, but this isn't talking about, you know, major capital outlays. The second reason is fear is a great motivator. You know, the internet architecture has resisted change. And Mark Handley has this great essay on, you know, why the internet just barely works. And his reasoning is, you know, sort of, you know, basically, why should it change unless it has to? But what's implicit in his essay is that there's no alternative, that the internet is just there. There's now an alternative. You know, if you talk to the clouds, they basically think that 10 years from now, the internet will just be the last mile and they'll be providing all the networking. That's clearly their vision. So there's now an alternative. And so the internet has a simple choice. It either changes or it shrivels to being a last mile provider. And we think the extensible internet is one possible change that will preserve its role. And the third reason is that EI is based on a simple conjecture that in-network support for applications, it's important for current and emerging apps, can be done at service nodes rather than each router, can be done in software, not in hardware. And the point is the private networks have proven every aspect of this conjecture. They're up and they're running at scale, they're running with real traffic at unimaginable scale. So EI is really the architecturally coherent version of the approach these private networks have already proven to work. So that's why we think it might succeed. So my last real slide is, you know, where are we? We built a prototype, really. Murphy Macaulay, who has built the prototype while teaching 4 classes a week. So progress has been a little slower, but, you know, we want to finish development, which should be in a couple of months, deploy it on Fabric and other test beds, engage the community by providing this test bed where we say, if you have a new service, we can deploy it. If you want to write applications on top of these services like PubSub or whatever, you can do that too. Continuing our discussions with industry, and we'd love to have your participation. You here, meaning as individuals, as a research group, or the broader community. With that, thank you, and I'll take your questions. And Eve, why don't you kick it off?
Sure. Actually, I wanted to just give Adrian the opportunity to ask his question. He's first in queue, and then there were some interesting questions in the chat that I encourage people who wrote them to get in line to queue up as well. Adrian.
Thank you, Eve, and thank you, Scott, for this. As you said, the second time I've sort of heard this, and finally it's sinking in a little bit. My question, which draws on some of the stuff in the chat, is about the layering here, and in particular the relationship with transport protocols. So in your very simple example of source SN dest, would you see the transport protocol running end to end, so source to destination, or would you imagine that those transport connections are terminated and restarted at the SNs?
So there will definitely be an end-to-end reliability layer. And because for reliability, we want the failure of a service node to be no more serious than the failure of a router today. So there'll definitely be end-to-end. Whether the pipe that goes, we view that IP is providing a pipe. Whether the pipe that goes between these two implement some kind of reliability is an open question, but it's not mandated by the architecture. the essential transport is end to end. Where congestion control is done is a much more complicated question.
Right, because I think this sort of factors into things like transport layer encryption as well, and whether the SNs are able to access the data to do anything unless those transport sessions are terminated and restarted. And this is kind of making me wonder. I don't dispute at all all your points about needing to introduce some additional layering to get the development. And I'm just wondering whether this is really should go in at layer 4.5 rather than at 3.5. But I'll let others talk.
Well, I mean, this is a very active area of investigation for us. And our current thinking is that the end-to-end, first of all the pipes will be encrypted at the low level, but that's trivial. And service node to service node pipes. But at the end-to-end transport layer, there will be encryption, but we want to have an option for the endpoints to say, here are the parts that we are willing to let the intermediate node see, versus here are the parts that they can't. And so they can decide, like, they want to take care of, take advantage of caching, then they might expose certain aspects. But if they want to keep certain material private, they don't. And so we want to leave that flexibility to the application itself. Does that make any sense, Adrian?
Yeah, thank you. And I kind of take that as this needs to be thought about more and nail down the details.
Right, but what I would say is I don't think there's a single answer that is mandated, but there has to be some flexibility.
Uh-huh.
Okay, why don't we, Dirk Trossen, you're next in the queue.
Yes, thanks, Scott, for the presentation. Similar to Adrian, some things that I heard again just slowly sunk in. And there was one issue that I stumbled across, which is the SN must implement public services. We need to agree somewhere, possibly in the IETF by governance. Isn't that a barrier to entry, though? I'm not really quite understanding the reason for doing so, because also the Kutscher asked the right question: who has the incentive to really deploy this? But if I have to ramp up my SN deployment by really essentially running any public service over it, isn't it preventing me for just quickly roll out my own SN where all I want to do is run my service on it because it's a low barrier to entry?
That our point is that once you support the execution environment, implementing these other services is simple. It does require extra resources, but if you don't make it uniform, then the internet, the beauty of the growth of the internet is you knew wherever you plugged in, you had a set of services you could depend on. If we now go to the space of IP options, which is no fun, that's not going to work. And so that really is critical to this, that you can build an application that relies on a public service, and that will be available wherever the user is. So that's a critical part of the proposal. And given that it's not about changing equipment, it's just about the scaling of your service nodes, we think there's a chance that that's going to take off.
So maybe I misunderstood your slide then. So you're saying because of the standardized execution environment, you can run any of the public services on any of the SNs that have been deployed, but I don't. So if somebody comes and wants to run a public service on my execution environment on my SN, it will just simply run because it's a standardized execution environment. It doesn't mean I have to provide it as a catalog of possible services I could run on mine. Somebody can just load the app onto my SN and it just runs.
No, it is let's say it's the IETF. The IETF decides what the standard services are. Every service node that claims it's supporting the internet has to run all the services. It's like once it's standardized, within 2 months, it must be up and running. That's just the rule. So it's not like somebody asks you to do it. If you're either a cloud who's supporting this or a carrier who's supporting this, that's the rule, that it just automatically updates.
Okay, thanks.
David Ran.
Scott, just talk for a second about what you think the service composition model is for this.
Ha ha. That's the service model, composition model.
What? Thank
There
you for
isn't.
your attention.
No. What I mean is we specifically do not allow users to arbitrarily compose services. That there will be sort of sets of approved compositions that work, because we think it is an impossible way to provide a general rule for what can compose with what. So yeah, that is one of the things that if you want to, you can't just say, well, I want services 28 and 37, because, you know, what if it's some security measure that's point to point and the other one is a multicast? So that we actually sort of proactively say that kind of linking is done at the definition of the services level, not at the user linking them together. So there might be like a particular stack that says, okay, you're going to get an IP-like service, and on top of it, you're going to get this kind of transport service, and on top of that, there's going to be this kind of DDoS prevention, and you know, whatever, as a set of what we might think of individual features, but it'll be a single service so that you don't have to manually compose things. And the market will show us what, you know, how that rolls out. But we really sort of discretion is the better part of valor, decided that taking on general composability was going to be a losing battle.
So then one quick follow on, which is, okay, so from the point of view of the user, they see, you know, a composed service as what they talk to the service node about. What about the internal communication among services? Is it some sort of private interconnect? Is it part of the architecture? Is it something like service chaining or VNFs that we see today that are so messy? Any thoughts?
Yeah, so in our current implementation, what we would do is we would say, well, if this is the composition, then we would have that ball of code. I mean, take those several different pieces of code, merge them together, and then have them run as a single service module, so that we've actually made sure that these the code bases work together. And so we're not doing NF chaining. It is actually, we decide to put we won't be using VMs probably, but if we were, we would put it in a single VM so that it's a single coherent piece rather than dealing with the nightmare of service chaining in these clusters.
Great, thanks.
Okay, would you like to go? You're next.
And it looks like an interesting topic to me, and it also reminded me of two things. The first one is service function chaining, SFC, and the next one is SD-WAN. So I do see that these two service have the same or similar model of this EI network. So what's the difference or any relation between the SFC and SD-WAN and EI? Yeah.
So I think for both of them, it is the extensibility. So for service chaining, you tell it to go through various boxes, but it's not, the network is not making you a promise of, I will deliver multicast packets for you. It is, go through this box. This box can do something, but service chaining doesn't give you any global service definition. That's your job. You have to sort of, you know, if you say go through a firewall and then go through this and go through that, you're the one figuring out eventually what that's giving you. So I think that's the difference. So something like DDoS prevention, that, you know, we're architecting it to provide, it's a service-wide thing. It's not just a single box. It's not just a scrubbing box. So that's what I think the key difference is. I don't know whether that helps.
So yeah, I may need to read more of the details. Yep.
And there's a pointer to the paper. I think it's got, can confirm, I think it's is it an April CCR paper?
Yeah. Yeah.
And, but we have a pointer in the agenda and slides. And I see there's one other person who's joined the queue, Tianji.
Oh, yes. Hey, Scott, it's a good presentation. Here, I have one thing to ask about your EI here. You know, it's running on the IP, and the IP normally has some protocols to communicate among all the entities. So for your EI as 3.5, so how does one EI node in your term to communicate with others? Or will you configure, or will you through some random, no, not random, some centralized controller? Those type of things. In that case, well, I don't know what the difference from the SDN model, something like that. Thank you.
So yes, we will have some kind of discovery process for service nodes to discover each other. But if you want to have an SDN-like control for a domain to have the service nodes know about each other, that would be fine. So the control plane, I was completely silent on the control plane for this. We're open to a wide variety of how you're going to manage your domain. Obviously, SDN-like approach, you know, for knowing where all the service nodes are and telling them how to reach each other would be very easy to do and probably the right approach.
Thank you.
That's everybody in the queue, but I wonder, I know there's a very thriving conversation going on back and forth on the chat. Is there anybody from there who would like to introduce?
I think we're getting so late, Eve. We need to send this to the chat and offline to the list because we're already.
So, sounds fine. Scott, thank you so much for coming in and initiating the discussion about this. No doubt there will be further conversation. So thank you very much.
Okay, thank you all, and please feel free to contact me if you know whatever's going on in the chat. Let me know if there's anything I can help with. Thanks very much.
And you have access to the chat, so you can peruse what's been stated there, and the chat actually gets posted after the fact. Okay, Wenfei, over to you. You're our next presenter.
Here we build our work in data center, so we have the flexibility to customize everything. It's different from the internet. I'm happy to introduce our work in network aggregation for multi-tenant learning. So this is a joint work from colleagues from Tsinghua University and the University of Wisconsin-Madison. Machine learning algorithms is used in various scenarios such as natural language processing, computer vision. So with the increasing size of the data set and the model, so the algorithm is implemented as a distributed system. So the PS architecture is a typical architecture that can support this kind of distributed system. In the PS architecture, the data set is partitioned and put on multiple workers. So in the iteration, in each iteration of the algorithm, each worker would compute a gradient. All workers' gradients are aggregated and used to update the model. Then the algorithm get into the next iteration. In the PS architecture, all workers' gradients are sent to a parameter server, get aggregated, and the result is sent back to each worker. So this kind of many-to-one transmission could possibly cause bottleneck in the transmission. So there are studies showing that the performance degradation of such kind of bottleneck. So recently, the chain of in-network competition provide an opportunity to solve this problem. The programmable switches offer in-transit packet processing. So the switch pipeline has registers which can store the in-network states, and the user-specified programs can be loaded to customize the packet processing. So there is an opportunity to move the gradient aggregation into the network, which can reduce the communication and consequently the overall training time. There is an existing work that applies in network aggregation to distributed training, switch ML. This work targets a single rack setting. So there is a rack connect multiple workers. So the switch is offloaded, the PS is offloaded to the switch. So the workers' gradients are aggregated in the switch. To support multiple jobs, the switch resource is statically partitioned and assigned to each job. So we think this in-network aggregation can be further improved because in model training, the algorithm takes apples to compute and communicate in each iteration. So for static allocation, when the job is in computation time, this switch memory would be a waste. And this design assumes the topology is a star topology with a switch in the middle connecting multiple workers. So it should be extended to multi-rack setting. For example, in bird training, there are tens or hundreds of nodes which cannot be put into a single rack. And in addition, static partition add complexity to integrate the switch memory allocation with the control plane. So we propose our solution with 3 key goals. The first goal is we should maximally use the network aggregation for performance gain. Targeting the production network, the solution should support multiple simultaneous job training efficiently, and it should also support a multi-rack topology. We design our solution, ATP, short for Aggregation Transmission Protocol, with the multi-tenant and multi-rack as the requirements. And we additionally solve extra problems which can further improve the performance. So in ATP, the switch memory is organized as an array of aggregators. Then each job has a job ID with multiple workers, and each worker has a sequence. Each worker's gradient is organized as a sequence of packets. So to support multiple tenants, we do not statically partition the switch memory. Instead, we organize it as a whole array as a shared resource pool. Then for aggregation, each packet is randomly hashed to a unit aggregator. So the aggregator assignment uses a hash function to hash the job ID and the sequence number. So for packets from one job with the same sequence number but from different workers, they would be hashed to the same position and get aggregated there. So the aggregation result is sent to the PS. Then the PS return the result to the switch. It would do 2 things. First, it would deallocate the switch memory. Then the packets is multicast back to all the workers. So we also overcome 2 challenges. First, because the aggregator assignment is decentralized, it's possible to have hash collisions. For example, job 2's gradient the packet is assigned is hashed to an aggregator, which is occupied by another job 3. In this case, all the packets would pass through the switch and arrive at the PS. The PS do the aggregation and send the result back to the switch. The aggregator is not deallocated, but the result is sent back to the workers. So the switch aggregation service is best ever, and the PS provide a fallback to handle the corner cases. There is another case of inconsistency or membership inconsistency. it causes incomplete aggregation. For example, the first packet is sent to an aggregator, which is reserved by job 3. Then this packet it passes through to the PS, but at this time, job 3 completes its aggregation and deallocated the switch memory, the aggregator. The remaining packets is sent to the aggregator and aggregated there. So both the switch and the PS have a partial result. They are waiting for each other. This is a deadlock, and what's worse is that there is no return packet result to deallocate this switch memory, causing memory leak problem. So we design a retransmission at the end host with the duplication in the switch. So for packet A, it is stuck at the switch and the PS, but its following packets may be successfully aggregated and returned. So if the sender observed 3 duplicated ACK, the result packet, it would retransmit the missing the packet that is missing the result. All the workers would retransmit A. So the aggregator has a bitmap to track which worker has already participated in the aggregation. So A2 to AN would not be aggregated twice. It would be deduplicated. And A1 is added to the partial result. So we get a complete result, which is sent to the PS and replied back. So with this design, we have a correct protocol that can guarantee the correctness. To support micro-rack aggregation, we need a aggregation hierarchy in the topology. Ideally, this aggregation hierarchy can be of many levels. We consider the data center topology. In the data center topology, the core network has multiple passes, and it uses non-deterministic routing. So it's not easy for us to pre-compute the hierarchy in the topology. So we only implement the aggregation in the core switches because there are waypoints that the gradient packets must traverse. Currently, we have a 2-level aggregation design. So all the packets would aggregate at the workers TOR first. Then they are sent to the PS TOR, and the second level aggregation is happening at the PS TOR. The final result is sent to the PS. So in this multiple rack support, we also overcome another challenge because the higher level switch. This is the hierarchy, aggregation hierarchy of the previous in the previous page. So in each aggregator, we have a bitmap which where each bit denotes one of its children. So there is 1 bit for in the switch 2, which indicate the switch 0. But 1 bit here cannot denote all the possible aggregation states of its worker because there are 2 workers. There are 4 possible aggregation states. So we overcome this challenge by falling back to the PS. We use the 1 in the higher level switch to denote the successful aggregation of the whole subtree. And in all other cases, we regard it as a failure and send it to the PS, fall back to the PS processing. So the previous design also overcome other challenges of reliability. When the retransmission with deduplication can also handle the packet loss correctly. And when packet loss happens, the end host would retransmit, and the bitmap in the switch can guarantee there is exact once aggregation. And we also redesigned the congestion control. The essential problem is what should be the congestion signal, because many packets are consumed in the switch, so they do not have round trip time. So there is no RTT. We use ECN as the congestion signal, use AIMD for congestion control. And on the end host, the switch can only compute on integers. it does not support floating point arithmetic. So we do quantization. We scale the float points to integers by a scaling factor, and because we scale the floating numbers, it's possible to have overflow at the switch. To handle this problem, we just use the fallback mechanism. We reuse the fallback mechanism. When switch detects an overflow, then host would fall back to the PS aggregation with floating point arithmetic. So we implement the user space networking stack in the hosts, and we implemented the in-network aggregation service in the switch. So in the evaluation, we have 9 servers, so 8 of them are workers and 1 as a PS. We compare ATP with other baseline architectures, such as PS architecture with different networking stack, and the ring or reduce architecture with different stack. We use training throughput and time accuracy as the metric. We run workloads of models in ImageNet contest. For a single job, we show the performance of a single job. So we run different models and measure the training throughput. We compare different architectures in each group. We have 3 observations. First, ATP in all model training, ATP outperforms other approaches. Sometimes the performance gain is very significant. ATP can benefit the network-intensive workloads more than the computation-intensive workloads. And comparing ATP with the ring or reduce with Harvard acceleration, ATP is slightly better than ring or reduce. But more importantly, it only uses half of the bandwidth than ring or reduce. Then we show the performance of multiple jobs. We compare ATP with the static memory allocation. In the static approach, we evenly partition the switch aggregators.
Wei-Fei, are you close to conclusion?
Yes. So
Thank you.
Yeah. Okay. So we tune the switch memory for 3 jobs and get the throughput, the peak throughput. Then we reduce the memory to cause contentions. We can see dynamic allocation degrades more gracefully than static approach. Okay. There are more evaluations. So in ATP, we co-design the host and the switch logic. The switch service aggregation service is best effort. It has dynamic resource allocation. The end-host networking stack has fallback mechanisms for correctness guarantee and also reliability and congestion control. To ML jobs, such a design can provide performance gain and correctness, and we achieve our goal of multi-tenant, multi-job support. So there is takeaway. So usually when we do in-network computation, usually we can get a very significant performance gain. Switch computes much faster than a server. But correctness guarantee is usually difficult because in-network computation introduces new semantic into the network. For example, packet can be consumed instead of lost. The end host need to distinguish these cases. And usually we do switch and host co-design, so we can get both correctness and performance gain. So for different applications, we can make different designs. That's all about my talk. I'm happy for questions.
Thank you very much for this. I think we are, it was great. The first discussions were great, so we're losing a little bit on time. Maybe we can send all the questions to your paper, either on the chat or on the mailing list. Thank you very much for this. And Dirk, you're next.
I need to stop.
Okay, let me see how I can get to my slides. So I'm trying to show the slides that are uploaded to the data tracker. Do you have to put them up, or how does it work again? It says no slides available. You know what? In that case, let me do screen sharing.
Here you go.
Thank you. Using my slides. Okay, great. Okay, yeah, thanks for inviting me. It's great being with you again, if only virtual, but let me tell you about some recent work on a system that we call information-centric data flow that is a product of our Piccolo research project that investigates new ways for integrating computing and networking. So in some sense, this could be seen as a customer to a system like the one that Scott talked about. So let's see. This joint work with my students Laura Alvedani and TM Ryan Gears. So in COIN, so far, in my view, we have mainly been discussing like two strands of work. So like one is coming from like data plane programmability, and then seeing how this could be put to a useful purpose for having distributed applications and improving their performance and so on. Maybe also evolving some protocols to support certain use cases better. The other strand, you could say, is coming a bit more from the distributed computing world, where we see, okay, what can we learn from distributed computing and how does it affect our view on networking, and maybe then reimagine the relationship and in the end have more programmable systems, also like the ones that Scott talked about. And so I think the thesis of this group in general is maybe is there some confluence at the end of these two strands. So this work here is more on the lower strand here, and so this is a paper that we presented at the ACM ICN conference this year, and there's also an associated demo, and so I hope to get you interested in this, and you can. I invite you to check out the paper and the demo video after this. So in distributed computing, we know that there are many different types of interactions. So like simple message passing, remote method invocation, data set synchronization, key value stores, and so on. And so I think some IETFs ago, we presented a system that we called compute first networking that was essentially a Turing complete, really general distributed computing system based on ICN. Today I want to talk about a like comparatively simple abstraction, so data flow, which is really a structured, direct basically graph-based distributed data processing approach, where you have a system, say nodes in the network, and data objects that are sourced at some endpoint or at some node trigger computation at other nodes, which then leads to new results that trigger computation somewhere else. And so this DAG here can be implemented in different ways. So you could say, because this model is so simple, and so if your application semantics allow it, you could also say you want to parallelize the execution by opening up a second subgraph here, and then just run everything faster if you have the resources, for example. So what you have is something like the data flow specification that could be laid out in the network in different ways, different levels of parallelism and so on. So the semantics in this case here, in this like word count example, would be that you split the input here in this text to lines box. But you can also have other use cases where you reuse the same input for different types of computation, of course. So some concepts. So data flow this fundamental paradigm can be used to implement batch as well as stream processing. So in stream processing, you like conceptually, you look at each data object independently in an unbounded stream of data. In batch processing, you group data, and typically the systems allow you to implement groupings dynamically, so based on some predicate or some time window specification and so on. So windowing is a common concept here that allows this grouping and slicing. And this can also lead to situations where you have something like a predicate that allows you to put like one data object into like multiple windows for like consumption by different functions, for example. But you can also split this up in different ways. Time is an important concept. So you can imagine that the whole system has to be kind of elastic. So you have often asynchronous data production. You can't really predict the processing transport delays and so on. And typically what you try to achieve is that you match the production rate with the input rate. And so the task of a data flow system then is to adjust the processing graph to your application requirements and the data production rate. And you can see there's all like some kind of variable performance, and systems can be compared how well they maybe keep up with the offered load, perhaps. There are a couple of really widely used implementations. So Apache Beam is basically the unified programming model that many data flow implementations use. So sometimes they are called runners. So you may have heard about Apache Flink, Spark, of course, Google Cloud Data Flow is a product, and so on. And the picture here on the right-hand side depicts the architecture of a system. I think it's probably inspired by Flink, where you on the bottom here you see the nodes. So these what is called task manager here. So this could be something like a compute node in your network, which is offering several slots for computation. And this, like the job manager on the top right here, is kind of orchestrating this whole system. So it's kind of having an overview about the available slots, and is responsible for allocating tasks for certain jobs, and then also managing the connectivity between those jobs. And so in Flink in particular, of course, performance is also an important topic. So Flink just had their annual Flink Forward conference recently, and there was quite a bit of work on trying to reduce buffer bloat and improving elasticity and so on. So fundamentally, this is not so easy because, for example, Flink is really using a connection-based approach to connect these task managers. And so it's not connecting the tasks, but really the nodes, if you like. And so these are like tunnels. And so the Flink task manager is basically tunneling all the, configuring the tunneling of all the task communication inside these connections. And of course, this needs some control, so like credit-based schemes, for example, to reduce buffer bloat or queue sizes and so on. So fundamentally, this is not a trivial task. So when you've been looking at this, we find that, well, these overlays do not match the inherent logic of like processing immutable data objects very well. So as I presented, the data is really locked into connections, and these are like virtual channels between hosts. And you always need this orchestrator tracking the resources and mapping the task relationships and so on. And so you treat the network as a black box, and then you tunnel the task communication inside virtual channels. And this makes it difficult to have a really agile matching of like your compute performance with the network performance and having also really responsive systems in the end. You don't have this full visibility of both the computing and the networking resources. Now in the system I wanted to talk about today, so we call this ICE flow, information centered data flow. We assume that we have a network of nodes, and in ICN we name everything. So the assumption here is that we have a network of named nodes, and there would be some routing infrastructure that allows us to discover them and forward interest packets and data packets in the system. And so on top of these nodes, we would instantiate functions also with a certain naming convention. They would also be announced in this routing system, and so we'll be able to construct compute graphs. And what we do in this system here is that we are kind of not establishing connections to functions or to nodes. We are actually just asking for input data. And so when there is new input data, this triggers computation at the downstream function and so on. And in this system, we are able to, for example, split up the computation as I showed before, but also have something like a multicast system where we kind of reuse the same data item in like ICN idiomatic way quite efficiently. So in ICE flows, we just talk about names for the infrastructure and for the actors in the system, and the computation of the actors, they return named data object with the usual ICN properties. So they are immutable, they can be cached, and they can be authenticated, encrypted, and so on. And so the interesting challenge here is that we have asynchronous data production. So we have to know when data is available. So like push semantics, which is typically not idiomatic in ICN. And then you have to think about flow control. So how do you couple consumers and producers? And then in the ICN system, typically you publish data. That means you make data available. So one challenge here is that you also have to know when the data has been consumed, which normally you don't really know, because requests can be answered by caches and so on. So there needs to be a system basically implementing a bit of tighter coupling as well. So the system has a certain naming convention where we name the application, the data flow actors, and then the produce data objects that the functions produce, and with that we are able to set up the system. And so this tasks of making data available and learning about new data, we are using an ICN technology called dataset synchronization for that, where so logically the producers produce data under a known prefix, and consumers can subscribe to that prefix, and then they would learn when there is new data under that prefix, and then they can decide, okay, I'm interested in text to lines object 1, and then I can fetch that. So there are implementations of this concept like psync in ICN, which in NDN, which you may have heard about. And so that means, so on the very low layer, that means consumers have to kind of send update interests to learn about new names periodically. And then from an application perspective, it's quite a convenient interface. So it's a bit like reactive programming. So you just get notified when something shows up that you are interested in. We implemented a few additions to make the system a bit more scalable, like to have less updates. So we have a grouping concept. where we group data objects into windows, and we're actually just publishing these windows. So so we're using ICN manifests for that. And so there's like a two-level indirection scheme here that makes the whole system a bit more efficient and a bit more scalable. I'm almost done. And so in addition to the data flow communication, we also need to share some runtime information and configuration information. So what is the static flow graph? What is the actual dynamic flow graph? What are available compute slots in the system, and so on. But also implementing this loose coupling between consumers and producers. So we have conceived something that what we call consumer reports, where basically we publish or what windows have been processed by each consumer. And so this is also a hierarchically organized data structure in ICN way, and we also use this data set synchronization scheme to share this information. Okay, just very quickly, so this approach allows us to deal with congestion control and like a proper receive window configuration in a different way. So we can really adapt like the interest rate, for example, to our actual processing speed, so avoiding that we ask for too much data that we cannot process in real time. And observing the performance of my downstream consumers could be a trigger for an upstream producer to initiate scaling out, and so like creating a new subgraph. So if I'm constantly realizing that my downstream cannot keep up, so this is the trigger that we can scale the system. So there's a demo on this, please check it out. And yeah, wrapping up, so these data flow systems are really important. They're driving many data science applications today, and you can see also more coming up. So in the IETF this week, there was a BOF on a approach called PPM that is also using similar concepts. The current systems are quite limited because of their, say, overlay approach. So centralized orchestration, limited data sharing, and we found this ICN approach quite promising. So this data synchronization approach works reasonably well, but to be honest, we are currently looking a lot into performance optimizations for that. So there's a lot to do in reducing the overhead and so on. This system would basically need additional infrastructure, so like a name-based routing infrastructure, for example. And there are solutions for that that in principle work. But maybe in terms of research, this system could also be supported perhaps better by a routing system that gives you more information. So, for example, resource allocation information directly and not only reachability information. And so for Coin, we think this could be an example for like new protocol work. So not saying that this is the best way of doing this, or this has to be something that ends up in a protocol spec, but it's an interesting example. So how you can break up overlays and leverage systems like ICN to do that. And so today I talked about data flow, but you can imagine that other interaction classes could be promising as well. So other systems maybe like Kafka, like publish, subscribe, broker systems, and so on. With that, thanks for your attention. Are there any questions?
Thank you so much, Dirk. That was super interesting. And I just want to point people to, there's the, ICN paper and demo. And I also wanted to kind of go back to one presentation and remind people that his presentation and paper are available from NSDI 21. So I think in the interest of time, we will go forward in the program. We had segmented the program into, papers that have been published elsewhere, and that's been really fruitful. Thank you all for your presentations. The next section is going to be brief. It's sort of new ideas section, and then we're going to get to the drafts and draft updates, and then a new draft. So with that, I think I'll hand over the floor to Marie-José, who's going to introduce the MODA ideas on behalf of her colleagues.
I hope my screen, oh my God, what is this?
And I'm going to try the timer clock.
Yeah, but I have the great screen problem of Meetecho. Yes, if I can fix this. Why am I seeing all this? It's supposed to be just the PowerPoint.
There you go. If you could put that
You see
in
the
display
PowerPoint?
mode. We did for a moment there.
Oh, okay. So let me go back into PowerPoint.
You can also
You see-
select a specific screen versus your entire, there you go.
Well, that's what I can't find.
Oh.
Oh my God. Let me stop this. It's crazy. I cannot find the thing to choose only one part of the screen.
I see. Okay. Want to give it one last shot?
Do you want?
And then I can download in the interim.
Yeah, you seem to be better at this than me. I'm sorry. I know there's a way of doing only the part of the slide, but I can't find the button. Maybe if I close no, I can't close all my screens. Yeah, you should try it. I'm sorry, people. I can start talking anyway so that we don't spend too much time. The presentation is about MODA. It's currently a proposal that's been put together by a large group of people, and it's a European-wide project. And the idea started from essentially a lot of us. Actually, a lot of people on the MODA team will be once we see the slides are very familiar to this group because a lot of them are involved. And one of the ideas. Oh. My slides are coming. Thank you so much, Eve. And the idea, and we can go directly to the first slide you can go to the next slide, Eve, please.
Okay, just bring it in presentation mode.
Yeah, in mode. Yeah. So the idea started from this. A lot of us who work in IoT have a big problem and I think that it was interesting that a little bit of the Scott presentation touched it a little bit. Everything is very verticalized, everything is fragmented, and essentially in IoT, what people do is they put a sensor somewhere, they put a gateway, and they connect to the cloud, and they claim that the problem is solved. The problem is not solved because the minute that you want to start having applications and services and artificial intelligence that cover more than one thing. You're in your agriculture. Well, you may want to take decisions that are based on the market, but then how does that work when you need you need for that to know or how much disease do you have in your farm, or maybe what's the building temperature, because that will increase or decrease depending on the time of year or the time of day, and it will increase or decrease your production, which will go back to your modeling of decision. And now the minute you do that, well, you have people involved, you have a ton of different systems that don't talk to one another. Next slide.
Let's see if I can.
So essentially, in this fragmented environment, the application development has very, very important pain points. So all these fragmented systems that require overlays, multiple gateways, different cloud application, different cloud providers that don't talk to one another. And there's issues always of that in security and privacy, because there's data privacy, there's digital sovereignty, there's multiple customers who are involved, and it creates a big problem. At the same time, in this group, Coin, we started to think that the internet paradigm is much more like a computer board than a telephone network. And if we have a computer board, then we need an operating system. And the edge to cloud view that we have in MODA, where there's computing inside different nodes that actually collaborate with one another at different levels in the network, is one realization of this vision. And Eve, you're the one who said that the data is the fuel of the 21st century. And in such an environment, also for IoT and for all these distributed systems, data valorization is key. I think Scott mentioned that, you use open source approaches, and this is exactly what we want to do, because in fact, it is not the algorithms or the software that's worth a lot. It's actually the data itself. And so we want to make sure that we can actually maximize data valorization by acting on it inside the network. Next slide. So what is MODA? It's the operating system for a new distributed internet. I hope, Scott, are you still on? Maybe it's the operating system for the extensible internet. It provides an infrastructure that allows applications to be easily developed. And it has a lot of things that were discussed in Coin, and almost we have almost one draft per each topics here: discovery services, communications, and publish subscribe. We haven't talked a lot about semantic integration, but our friends in Things to Things have done it a lot. The implementation of common use functionalities that we need, including forwarding and forwarding to different CPUs, and forwarding not across just layer 3, but implementation of forwarding based on name. And so there's a link there to ICN and NDN. And also, obviously, in MODA, what we want to have, going back to the pain points, we would like to have APIs and tools for running running code across those multiple heterogeneous, oh my God, here's a typo, heterogeneous nodes inside the network. Next slide. The format didn't work very well here. The main MODA functionality, I don't want to go, I'll go fast because I don't want to go into everything of this, but obviously we want to do some orchestration. There was discussion about orchestration before, but we feel that we can actually look into this. And again, on-device computing over a heterogeneous system, we want to have, if we can, as much as possible, reusability. And that's actually a problem on those verticalized applications, is if you change vendor or if you change supplier, your system doesn't work anymore because they use different protocols, different semantics, different everything. You would like to have modularity as a design choice. I usually, when I teach my class on distributed systems, I talk about the Lego blue brick approach, so that, we want to have a lot of Lego bricks, and we connect them when we need them, and we don't use them when we can't, or when we won't. And actually also in IoT systems, it's important because a lot of times you have limited resources. You want to be able to manage the network processing units themselves, so the in-network computation that allows the packets and the information. I would think I would speak more of information in this case, to be properly managed and properly sent to the right interfaces and the right end devices and end system. And obviously, we want to support data and intelligence services. More and more data-driven is actually the basic of a lot of networking. Last year with Henning Schunzrene, we did a study for the NSF on the future of broadband, and actually the conclusion was that everybody who does broadband wants data. So data-driven may require to have new features inside MODA and inside the network itself. And of course, there's AI that is not only in the applications, but more and more in the network in terms of network management and even management of loads inside data centers and elsewhere. Next slide. I think it's almost the last one. Yeah, I think the previous slide is an overview of what it looks like, but the picture is not very good, so we can skip it. The link to the Oinrg, well, actually, again, it's not just that there's a lot of people involved in MODA that are also members of this community. It's actually, there's a lot of common research topics. I mentioned discovery. We would like to discover storage, functions and computation. So functional discovery, storage discovery, computation discovery. We would like more and more, I think both, and that's actually since I have two hats here, so I can say as maybe as a COIN chair, that distributed abstractions and protocols are also very important to both groups. Decentralized security and trust, obviously important, and there is going to be a draft update later in this talk about security, but it's also an important thing when you start distributed systems. Federated learning, we haven't really addressed that a lot in COIN, but it is something that we could look at because federated learning needs some form of in-network, maybe not pure computation, but at least some form of trending and connections and orchestration. And obviously there's all the use cases, and actually the people right after me will talk about use cases, so I won't go there. So this was a very short presentation. This is MODA. We know that this is right now being proposed. It's been evaluated. We don't know if it's going to go through, but I think the team, and I'd like to really acknowledge the architecture team that did this, and a few of them are on the call right now. This was an incredible effort. This was an incredible fun thing to do, and we're thinking that maybe we want to continue the work inside this community and outside. Thank you.
Thank you so much, Marie-José. There is a question on the chat asking if there are any pointers that you or others can share that would help people read more about, or if there's a website, for example. So in the interest of time, if we could take that to the list or the chat.
Yeah, I will. Yeah, I will see what we can share. I see this is from Daniel King. I will see what we can share. I'll ask the proposal management, which I was not one of. So thank you, Daniel, for this question, and I will ask. Thank you.
Okay, it looks like the use cases presentation is next. We're into the some draft updates, and I'm going to ask if folks could please shorten their presentations to 8 minutes each, just to kind of reclaim a little bit of time.
Yeah, I'll try to keep short. So let's see.
Oh, and actually, you know what? I see that I did take the advice of those on the chat window to load things into MeetEcho, which I hadn't done before. So I admit user error on my part. It says, okay, so do you know how to request the slides? Looks like you've done it.
I've already done that.
Ask to share the slides. Perfect. Thank you.
So that looks good.
Look at that. Perfect.
Yes.
Thank you for helping me out.
Yeah, so hi everyone. I'm Ike, and I'm here on behalf of all the co-authors now for the use cases draft, just giving you a bit of update what we've done since the last iteration. So the first thing you can already see on this slide, so we've a couple of new co-authors. So Xavier, David, and Miguel have joined us. Apart from that, let me first give or remind you again of the purpose of this draft. So in our COIN charter, we have this second item where we want to do research on use case driven requirements analysis, and where we also want to identify potential benefits to these networks from in-network compute functionality. And this is kind of what we're trying to do with this draft now. So until now, it was rather a loose collection of use cases, so stemming from the industrial ones right in the beginning. And yeah, now we've quite a few of them. And what we're now currently trying to do is actually go more towards providing input to the second charter item that we have there. Changes in a nutshell since the last iteration. So first of all, we have regrouped the use cases. So from the historically grown structure to the one that we have right now. So we've thought of 4 ways how we could think about the use cases. The first one are really kind of new user experiences that can be enabled using Coin. So the AR, VR stuff that Marie-José has presented quite a few times is, for example, in that category. The second group is supporting new Coin systems, so where we think that the new interaction between communication and compute can actually enable new kinds of systems, or so entirely new systems. The third category is on improving existing Coin capabilities. So we already have networks which use some form of Coin. And so, for example, CDNs have kind of already some Coin functionality in there. And those use cases are now really on how those networks can even be improved further. And then finally, we have entirely new Coin capabilities that can be enabled. As a second aspect, we've then also tried to sharpen and tighten the taxonomy. So it was not that focused before, and we've tried to do that now. I'll come to that in a moment again. And finally, we've also already started to prepare the actual analysis that we want to do later, mainly focusing on the research questions and requirements. So with that, let's have a look at the current draft structure. So what you can see is that we have actually done the regrouping already. We also have this one new use case provided by Xavier that he had already presented last time, or in our last meeting. And then also we have already the analysis in the structure right now. So we're only waiting to get started with that, basically. And then finally, the aspect that is at the top of this slide, so the terminology part, that we've tried to really start aligning the terminology across the different drafts and the other research group documents, so the draft by Dirk, which has been expired already, but yeah, we've tried to align that in some way. And that is the following now. So everything in green that you see on this slide is terminology defined in this draft by Dirk and the other authors. And we've tried to use that terminology throughout our draft as well, or actually, at least have started to do that. And we've then also added quite a few additional terminology that we thought might be necessary for our draft. And overall, our idea would be to sort of get an overall terminology all across Coin, where then the question obviously would be where would actually place that terminology. So whether we have that in every draft or whether we have one draft that collects all of that terminology. Then quickly regarding the use case taxonomy, so not that much that has changed here. So we have basically only split up the opportunities and the research questions so that they are now more clearly identifiable. We've also tried to link the description of the different use cases really to the new grouping that we have introduced into the draft. And finally, we've also tried to focus the requirements a bit more, really only on the Coin capabilities, so that we really describe or try to describe what the Coin capabilities themselves need to do, rather than what the overall use case has to satisfy. And with that, I'm already at the end. So next steps that we are planning to do is first finish aligning the use cases according to the new taxonomy. So really pinpointing the requirements and aligning the descriptions a bit better. Then we're also trying to think about the terminology that we're currently using, whether that's everything that we need or whether there are additional terms that we might require. And then also maybe as a question to the complete research group, where we would like to collect that terminology, as the draft by Dirk and Jörg, I think, has been expired some time. And yeah, that's just a matter of things where we collect that. And then finally, we would also like to start with the analysis. So we first try to condense the opportunities, research questions, and requirements, and then afterwards try to identify aspects similar across all of the use cases, so that we can then perhaps give a collected input into the second charter item of this research group. And that's it. Thank you. And I think comments, we can take them to the list if there's not that much time.
Thank you. I cannot really, I'm a co-author, so it's hard for me to be both co-author and share on this, but I think there will be a discussion amongst the chairs to bring this as an ORG document, but I'll let the other chairs talk about it since I'm an author. Thank you.
I'll just confirm that that does seem like an appropriate next step that we can discuss on the mailing list.
Okay.
Thank you.
Thanks
for moving this forward. This was great. Much appreciated. Dirk Trussen, you are next.
Okay.
We see you. We
Yep.
hear you.
I'm just
Excellent.
trying to get this up. And there you are. Good. You can see the slides, right?
Yes.
Very good. Still a bit new with the UI. Colin has given a good tutorial. Thank you. Transport protocol issues of in-network computing systems. That's another draft Ike, Klaus, and myself have been working on. It had expired initially in the last meeting because of the focus we had mainly on research presentations, and it's not quite as outdated as the date on the first slide gives. It was obviously presented at the 11th of November 2021 and not 2020. The premise, I highlighted the main piece. I don't intend to read this. So this is about what if you have functions of the communication system. Sorry, if the part of the end-to-end function may be provided as part of the communication system. That's the network premise really of COIN. This is a quote from the end-to-end paper, from the original end-to-end paper. And we're looking into challenges to the traditional end-to-end transport protocols, trying to outline opportunities, research questions for the design of transport protocols that may arise from the availability of in-network computing capabilities. That's the premise really, as a recap. So the intention is to provide insights into various transport technology areas, research questions challenges I already mentioned, ongoing efforts, and concepts that are currently under study. So we're not limiting ourselves only to existing RFCs, but we're also looking at ongoing work, research, whatever we can find. Outline possible future work in COIN and elsewhere. So that's starting with COIN, but doesn't necessarily mean that all of the work needs to be done in COIN, obviously, and provide that in a gap analysis. So the goal is to contribute to the objectives of COIN, and I mentioned, I quoted here the COIN Charter Scope number 4, namely the research and potential new transport protocol required or enabled by in-network compute resources. So that's a dedicated item in the charter, really. And we believe and hope that the draft contributes to that. The general structure, we made similar changes, a bit aligned in some sort of lockstep to the changes we also made in the use case draft that I presented, so trying to sort this a bit more into various areas of discussion. So in this case, for the transport draft, we divided or collected the separate chapters from before into a single technology areas section now. That's the section 3. So that has been entirely restructured, and everything has been was integrated under that section. And then started with the gap analysis. This is just to present the technology areas and the gap analysis more visibly in the structure. So there's added here for future extensions, and in particular with a possible formation of future needed work. So this is much more gearing the document towards the charter item that I mentioned before, right? So in section 3, so everything that really was before in the various, I think, section initially 3 to 7 are now all found here. And that also helps us then to link back from the gap analysis in section 5 into the appropriate technology section later on, so it makes the editing easier. There were smaller updates here only, apart from the larger structural change in section 3.1 by linking this to the ongoing in-area work on internet addressing, where there's a discussion going on at the moment. And the section 3 also added ongoing work in the ICNRG and in the BA working group. So these were content changes as well to the structural changes. Question obviously to the group we would like to ask here, and happy to get any ideas either in the chat or on the mailing list, is what research question related concept ongoing efforts. Our intention is really to also approach the community with that question specifically, and because we are sure that we're missing concepts simply because we're not aware of them, or we haven't worked through all of the various ones. So if you have anything, any research question and a related concept you want to share with us, please do so. Gap analysis, as I said, we added this with the same subsection structure. So you will see that the subsection structure in section 3 is mirrored in order to later really have a clear relation between technology areas, the 7 subsections we have, to the actual gap analysis in these various areas. At the moment, we only added an introductory paragraph outlining the intentions. We have no content in the individual sections yet. Question obviously also to the list is, or to the community is, to be one such section or not for COIN. So we believe that it may help us to working towards the charter. If we don't want this, we can remove it, but that was the suggestion we made, and that's a question we would like to get some feeling from the community. Future plans. So we mentioned already the last time, and we haven't really made too many changes to do that, but we want to, because we also made changes to the use cases. And I think now that we structure the use cases, as you could see in Ike's presentation, more clearly around the notion of capabilities, we want to also make clearer linkage to the use cases, and in particular with that taxonomy that's being used now in the use case draft in the next version of the transport draft. We want to add more existing work. We've already, there was a communication between the chairs. We unfortunately were a bit too late to bring this to the chairs. Work that has been presented at HotNets 2021, and Balaji, one of the co-authors of that paper, is actually, I hope he's still online, but at least he was online before. So we try to bring more existing work here, even to the point that we may also, have this work that we find present to the wider community. As I said, we were a bit late for the agenda for this time, so it may come in the January meeting. Also, similar to the use case draft, to turn the research questions maybe at a later stage into some sort of requirements language that would allow us to, formulate research work around these requirements. Gap analysis to fill this. I mean, if the question I asked before is answered positively, so we would like to have a gap analysis because it's useful to have that. We really would need help here, would invite contributors to that. And with the view on the charter, the question here, that was a bit of the confusion I had when because I thought the use case draft was an RG document already. I think it's the transport draft that isn't an RG document yet, which is why it's written on here to maybe adopt that as a potential key output towards the scope of the charter as an RG draft as well. That at least that was the memory that I had about the issue. And again, to repeat, we would really welcome contributors, gap analysis, related work, new work that exists, even if you just send us links if you can't be bothered to get it as a co-author into properly written up. We're happy to get any material that you'll find that you think is relevant, should be listed in the draft. Please do contact us to do that. If you want to become a bit more active in helping us, absolutely welcome. Certainly would need that, would want that.
Dirk, I think you're spot on in terms of what the future and next steps are. You have a question from Peng Liu. So Peng, if you'd like to jump in.
Yeah, Pony from China Mobile. Just one question. I see the draft mentions that therefore with downcast, so I want to ask that if the quick could be a a potential way to help the flow affinity or the service equivalence, since it has a fixed connection ID regardless of the change of address or port. Yeah.
Yes, yeah. So the linkage to Dynacast is still in the draft, even though I think the draft actually have expired, and there are aspects that are mentioned in the Dynacast work that I think would need to be pulled more properly into the draft. That's correct. So it's a little bit a loose issue at the moment in the draft. It needs to be clarified. Yeah.
Spencer?
Okay.
Yeah, I was just asking, and I'm seeing answer also in the chat, but a question about if there was a GitHub repo that we could contribute to, especially in the gap analysis. I think the gap analysis would be really helpful if you all could provide some insight there.
Yes, absolutely. Ike, thanks for putting the GitHub into the chat. I'd seen that. I couldn't type quickly enough. Yes, I would really welcome, and that's certainly a way to contribute to that. We do the same for the use case draft. There's a separate one for it.
Yeah, we that's really improved us to get input from contributors in other venues. So thank you.
Thanks. Yeah, appreciate it.
Thanks so much, Dirk. Really great progress. In the interest of time, we are going to move forward in the program. Let's see, we have the Enhancing Security and Privacy draft. And if you could condense your talk, I know we'd given you 10 minutes originally, but if you could cut it down to 7 or 8, that would be wonderful. Thank you very much.
Okay, I will try. And I also try to share my screen. Okay. Okay, do you see the right screen?
We do.
Okay, great. So yeah, thank you. You didn't hear from me in a while, but we still have a draft on enhancing security and privacy with in-network computing ongoing. And actually, a lot has been happening in the past months and year in this field of research. So before I go into the update, first a short recap about the scope and intention of this draft. So the main focus is to implement security and privacy mechanisms within the network, and the idea behind this is to reduce the latency and also to improve the scalability and provide a quicker reaction to security incidents, especially in comparison to middle boxes, which are typically used to provide security functionality today. And potential use cases for this are to retrofit security for resource-restricted or legacy devices, which cannot implement security themselves. And this might be also beneficial for industrial networks with high performance requirements, or to provide scalable and transparent anonymization. So the goal of this draft is to provide an insight into the potential of COIN for security and privacy, and to show research questions and challenges in this direction. As you know, this draft mainly consists of loose ideas, and these are split into 3 areas. So we first have protection mechanisms such as encryption or authentication.
Audio
Then we also have intrusion
or other people who have issues.
And last we had incident reappraisal, but we extended this to security-related network monitoring. Okay, now in recent times, we observed that the research community recognized the potential of COIN for security and privacy as well. So there is an increasing number of valuable publications, and in the latest draft update, we now added research-related work to provide practical examples for research and applications. And I will give a quick overview on the following, which I hope will help you to get a grasp on this topic. So first, we added related work.
We are having
to
audio
encryption
difficulties.
and security checks. I think I have some tone problems, but I hope you still hear me. Okay. So first, related work to encryption and security. Actually, secure cryptographic functions are not supported by current programmable networking devices by design, but there are efforts by researchers.
Sadly, Ina, can you hear us? Ina, can you hear us? We're having terrible difficulty hearing you. You're completely broken up. We don't, that sounded fine. I wonder if it's your headphone?
Usually I don't have.
Well, why don't you continue? So I'm just wondering, I don't know if anybody heard anything, unfortunately, because your audio problems started almost when you started presenting. I turned off your video to reclaim some bandwidth, but could you start again?
Okay, so.
And let's see if we have a little better luck. I mean, really, it's been broken up since the
now?
beginning.
Okay.
We do hear you now. But now you're showing that I think we got about one or two. If you could go back.
Yeah, well. Okay, so you didn't hear anything. That's that.
I think we were on your first slide. We didn't hear very much. This slide we lost entirely. And again, we're sort of pressed for time. So
okay. To make it quick.
Let's start again.
Yeah, sure.
Maybe in condensed form.
To make it quick, the focus is on implementing security and privacy mechanisms within the network, for better performance and faster reaction. And use cases are, for example, retrofitting security for restricted devices or for network with high performance requirements. In recent times, we observed that there is an increasing interest of the research community. So there is also an increasing number of valuable applications in this field. And now we were able to add recent related work to our draft, which provides us with practical examples for research and applications. So I will give a short overview of this in the following. And hope this helps you to get a better grasp on this topic. And first, we added related work regarding encryption and integrity. So, secure cryptographic functions are not supported by current programmable networking devices by design, but there are efforts by researchers to fill this gap. And so, Shen et al. Implement AES encryption with scrambled lookup tables, import-based hardware switches, and similarly. Okay.
Ina, I think we're going to need to defer your presentation. Every time we actually speak, it's fine. But then as you present, the audio is really broken up.
I understand. That's a mess.
Sadly.
I'm sorry.
Really too bad. Yes, I know Hannes is saying he really wants to hear this, as do the rest of us. And now as we converse, it's fine, but as you go into presentation mode, it's completely broken up. So I think we're gonna, yes, it's very strange. I wonder if it has something to do, I can't tell whether you have a headphone or not, but.
Is there maybe a way that you could just share the slides for her in case it's the slide sharing?
I'm gonna have to, did somebody already have it down? Let's see, how do I display it if I have
Because
it
it really seems like
it.
we can hear her perfectly well as long as she's not doing slide sharing.
Okay, let me download and let's see. Where do I go to get the, okay, so I uploaded everything to manage the slides. And then if I want to show this.
There should be a share button on the left-hand side near the near where you mute and unmute on the left.
Where are you? I think I'm not seeing it.
It's right next to the screen share button.
I'm just not, hang on. Oh, got it. Sorry. All right. New user here. Share. Okay. Are you all seeing it now?
I think so.
Okay. All right, let's start this again.
So you again missed everything.
Yes.
Yeah.
And we only have 5 minutes, so I think if you could just give us the high level, and we're going to have to punt on other presentations, sadly. Go for it. We'll give you the
Yes,
last 5 minutes, and we'll take the very last minute for
yeah,
us.
then yeah, the next slide.
Tell me which slide
maybe.
to start with.
Yes. Okay. So yeah, very quickly, there is work which tries to implement encryption, also secure cryptographic functions for encryption and hashing in the data plane. So this lays the foundation for security and privacy applications, such as implementing security standards, for example, IPsec or MACsec in the data plane. And it might also allow for onion routing or message authentication in the future. The next slide. Yeah, there's also an effort to implement authentication in the data plane by offering basic mechanisms like port knocking or one-time passwords. And this might allow for continuous authentication without latency overhead or additional middle boxes. Then next slide. Other work is about allowing scalable, transparent. Yes, no problem. Yeah. So other work is about implementing scalable, transparent, and lightweight anonymization in the data plane. For example, by rewriting source addresses and hiding path information by using randomization, or encrypting IPv4 addresses to obfuscate traffic. And the idea behind this is to address the performance and usability issues of existing anonymity tools like Tor. Okay, then next slide. Yeah, we can also use computing in the network to improve intrusion detection. One potential here is to allow for inline detection and a quick reaction to anomalies, but we can also reduce the load on existing intrusion detection systems. And this is exactly what Lewis et al. Do. So here they apply rule-based pre-filtering in the data plane. And by that, they achieve a traffic reduction of up to 75% at the actual IDS. Okay, next slide. And last, we looked into network monitoring, which can be, for example, used for network forensics. And here, Sonchak et al., for example, proposed flow monitoring on P4-based hardware switches. So they pre-process packets in the data plane and then very efficiently create flow records in the control plane. And this offers a high-performant and cost-efficient alternative for accurate flow monitoring in comparison to existing solutions. Okay, the next slide. Yeah, so to conclude, we see increasing interest of the research community, and that underlines our intuition about the possibilities that COIN provides for security and privacy, and also its relevance. And this is confirmed by recent publications which match the ideas of our draft, and they're published at high-ranked values, for example, Usenix Security. And existing work also provides first proofs of concept, which show that implementing security in the network is actually feasible. So we derive from these observations that enhancing security and privacy within network computing actually turned into a hot research topic, and there are many exciting ideas left to investigate in the future. Therefore, this draft underlines the potential of COIN to benefit diverse and quite significant applications, which also go beyond typical networking. And yeah, to drive this draft forward now, we are strongly looking for your feedback and also contributions. So if you're curious about this draft or have any comments, just drop me an email. And otherwise, I thank you for your attention, and I'm looking forward to any inquiries. Okay, that's it.
Thank you so much. Really sorry about
Yeah, that's true.
the network itself got in the way of your presentation, but thank you for that terrific update
Yeah.
of some of the research that's out there. Any questions from the audience in our last minute?
I think there was a question in the chat before, but I can get to this offline.
Okay, that sounds good. Great. Then I will stop the slide share. Thank you so much for persevering, everybody. In our last minute, I think there are really two topics. One is just that if you don't know already that HotNets is going on in parallel this week, and there's some very interesting work. And the second point of interest is that, of course, we've been threatening to have an interim in order to review our scope. And I think we would like to do that halfway between this IETF and the next. So stay tuned for that. We welcome your inputs on the mailing list, and thank you to so many of you for sticking it out despite the network errors, for arriving at whatever hour it is in your time zone. Many of those time zones, it's an inconvenient hour, so thank you for being here, and to all the presenters for the terrific presentations. I know there's been a really healthy dialogue in the chat window, so I look forward to sharing some of that. We all look forward to sharing some of that in the minutes. So thank you once again, since we're at the top of the hour, for being here. Any other comments, Marie-José or Jeffrey? Okay.
Thank you very, very much, everyone. And yes, see you on the mailing list, and see you in hopefully in person soon.
And thank you to those who helped handhold us through some of the user interface issues. That was greatly appreciated in real time. Thank you. Have a great day, evening, afternoon. Bye-bye.